So Otmar Schmid from the Helmholtz Zentrum Munich. I'm giving an introduction on the role of tissue-delivered dose and dose metering for hazard prediction and risk prediction. So here's an outline of what I'm trying to do is we basically start with in vitro assays and animal models preclinically, and we want to predict what's happening in humans, so human health effects. And we all realize there's a huge gap. The unit.
You're breaking up. I can't hear you.
Unbelievable. All right. Can you hear me now?
Yes.
Okay, great. So what's linking those two levels is the tissue delivered dose from both sides, yeah, from the preclinical and the clinical part. So we need to generate these dose response relationships based on tissue delivered dose. This is really strange, sorry. And how to do that? So we typically go with an exposure level, a concentration of some kind into the animals or the cells. Then we have to find out what is the delivered concentration, like to the nose of the animal. And then that has to be converted into what is actually reaching the tissue. So it's either the cell layer or the animal lung in this case. Then from that we get the dose response, and then we can identify no observed adverse effect levels or low observed adverse effect levels. And now we have this information, we need to go to humans. How do we do this? We basically have to make a leap of faith. Yeah, there's a huge jump now because you now have to account for the model human susceptibility factor. So is your model more or less susceptible, whatever you're trying to measure? And then, of course, we typically, because this is highly unknown, you add a safety factor in order to do that. Now you have a corresponding no observed adverse effect level for humans, and then you can work your way back up. From that, you can now deduce the delivered concentration and the exposure limit. Yeah, that's what regularly is most important, the exposure limit. And that, via epidemiology, can be then linked to health effects in humans. The most important thing, which I see often misjudged, is people think, oh, exposure level in cells or animals has to be the same as the exposure level in humans. And that, of course, is not the case. Yeah, you have to go through the tissue delivered dose. You have to go the cumbersome way from exposure level in your model to tissue delivered dose, and then you have to translate back tissue delivered dose into exposure limit human. But this can be done. The models are there. The understanding is there. So in order to explore these issues, we have used the nanomaterials from SmartNanoTox and applied it in different ways to animal models and cell models. The most data we have for intratracheal instillation, where you go directly into the lung, no aerosol, just instill directly into the lung. Then there is, we have an intermediate issue with inhalation. So this is also intubated mouse, but instead of instilling just a bulk liquid, we aerosolize the liquid into the lung with the inhalation. And here's, of course, the gold standard, the nose-only inhalation part. Yeah, and we all realize instillation is nice, quick, but it's not physiologically so relevant. While, of course, nose-only is very cumbersome, takes a lot of time and effort, but it's highly physiologically relevant. So we're stuck in between these two poles. And in the intermediate level, we have this now ventilator-assisted inhalation, which can kind of bridge the gap. It's much faster. Within a few minutes, you get the dose you need to get a response from the animal. So then we get the dosimetry, relatively simple for instillation and ventilator-assisted inhalation. It can be calibrated. For inhalation, you have to work harder. You have to do analytical analysis in the lungs, or you have to use computational lung deposition models. So now, what is the difference between instillation and inhalation in terms of distribution of material in the lung? That is shown here. So here I have a mouse lung, which we optically cleared. So it's transparent. And then sheet by sheet, we illuminate the entire lung. This is a non-dissected lung. then you can see the full image of the lung. Green is the tissue, autofluorescence from the epithelium, and then red are the particles which were delivered. And you see it's a kind of a patchy situation. Yeah, you get these hot spots, you get regions where you have no substance at all, just green. And then, of course, also in the deeper level, you don't get that much of material. Here is the ventilator-assisted inhalation, very different picture. So you get the aerosol all the way out to the periphery. Yeah, look here, there's nothing, for example, in the periphery. You get the aerosol all the way out of the periphery and very uniformly throughout the entire lung. Yeah, so this is a little 3D animation of the same thing. You can appreciate from different sides how uniform it is distributed throughout the entire lung. This big thing here in the middle, that is the esophagus, where the aerosol is cleared and ultimately swallowed. And yeah, as we go closer, you see it's really nicely uniform throughout. There's a few dark spots here. Yeah, you see we didn't get the aerosol quite there, but overall it's relatively uniform. In vitro models, we have different cell types. Of course, we have mouse as the main organism and rat. So we have mouse cells, epithelial cells, LA4, and macrophages, MHS, and co-cultures thereof. For rat, we have just the macrophage cell line. And as endpoints, yeah, what I'm focusing now is, as endpoints, is just viability to make my life simpler. But of course, we have more in-depth analysis. We will talk about that later, not me, some other people. And we also have a cell-free oxidative potency of nanomaterials, the DCFH assay. We have submerged cell culture technology, and we have the air liquid interface exposure, where the aerosol is deposited directly onto the cells. And for that, we use the cloud, VitroCell cloud technology. VitroCell is also a partner of this consortium. And with the integrated quartz crystal microbalance, we can exactly measure the dose delivered to the cells in real time. So for the standard submerged cell culture systems, you have to work much harder to get the dose. Here's a picture. The cells are here at the bottom. The red is the medium. The particles of different size are suspended. Then you start the clock, and you see the bigger ones fall faster than the smaller ones because of gravitational effects. And that leads basically to the problem that the nominal dose, what you put into the medium, is not what is delivered to the cells. Yeah, it depends on the size and the time and the filling height of the medium. All kinds of parameters are relevant, and you need to take that into account in order to get the true dose delivered to the cells. Here is kind of an overall schematic of what you're dealing with. So you have the size of the particles in the medium. You have a certain filling height. I'm using 5 millimeter, 24-hour incubation time. And then over here for the large particles, you have gravimetric deposition, 100%. If they're large enough, red is 100%. Then you go to smaller sizes, you get less gravimetric deposition, so you get lower deposition. And as you go to the really low particles, like a few nanometers, then diffusion kicks in, and again you get 100% deposition. But the crux of the thing is, typically we are operating in this regime, and here on the y-axis I have the density of the particle, and that is a convolution of the material density and the shape of the particle. And since we have agglomerates, yeah, the effective density is typically much smaller than the material density. And so typically when we do our experiments, we are in this window here, where we between 100 and 600 nanometers, roughly we have densities of up to about 2.5 grams per square centimeters. And you can appreciate from the color code that in this range you deal with 5 to 100% cell-delivered dose. So that's a factor of 20 uncertainty in dose, and that needs to be carefully considered. And you can do this, for example, with these ISTT particokinetics model. Yeah, so that we need to be aware of. Then let's turn to the dose metric. We have these 61 materials. It was already referenced what we have, mainly carbon nanotubes, half of them roughly carbon nanotubes, positive control, quartz asbestos, and then we have metal oxides and graphene and carbon black also as a nice reference material. And notice the breadth of parameters, yeah. So carbon nanotubes from 7 to almost 70 nanometers diameter, length from 0.2 to 10 micron, DET surface area, quite variable, and the same for the spherical particles. So we try to have a broad scale of materials and to study what's happening. So I start with the cell-free Ross assay on the x-axis, on the y-axis. Fluorescence is the readout for DCFH, and then you have the dose on the x-axis, the mass dose. And you see, of course, I have here multi-wall carbon nanotubes, several of them, Mitsui, asbestos. And they scatter quite a bit. There is some trend, of course, with those, but it's not that nice. And then if you convert this into square centimeters per milliliter surface area, then you see a very robust linear correlation, which indicates that surface area is a much better predictor of the Ross than mass. Yeah, the same happens for animals. When you do instillation in mice, we take the bile bronchoalveolar lavage, and then we analyze the number of neutrophils and normalize it to the total number of cells in the bile. And then you find this neutrophil percentage, which is a hallmark of inflammation. Here is the one-day data, so 1 day after instillation. You see again the BET surface area on the x-axis and the neutrophil response on the y-axis. And you see here the green bluish materials are what I call the nanomaterials without specific toxicity. There is multi-wall carbon nanotubes, titanium dioxide, carbon black, all kinds of stuff in there. I'll get to that later. And then there's just a few which have a higher toxicity. And these are basically quartz, zinc oxide, and some of the carbon nanotubes, the JRC materials 401, 403, and Mitsui. And then this guy here is asbestos, which has the highest toxicity. So you have like a 5 to 10-fold shift in hazard. Yeah, this is the hazard factor now. More hazardous, 5 to 10-fold. And they group nicely into 2 or maybe 3, if you count asbestos, 3 classes. And if you do the same thing in terms of mass, these are the same materials, you see nothing. Yeah, there is not a classification by any means. You just have to work with each material individually. There's no classification benefit from that. So you have to go to surface area to do that. Here is just a kind of we highlight the titanium dioxide materials, which we have like 17 or 16 of. We have the anatase, which is these blue ones, and then we have the rutiles, which is the red ones here. The red ones go very nicely with the gray ones, which is Printex. Anatase has a somewhat lower toxicity, acute inflammatory efficacy. And then there's the anatase tubes, which basically mingle with the rutile titanium dioxide. But overall, they're within a factor of 3. If you look the numbers here, so you have 200 square centimeters per gram, and anatase is like 550. So it's a factor of 2.5 to 3. This is what I would call is still within one class of toxicity. So what happens at a later time point, 28 days? Same thing. Here's BET surface area neutrophil. Here, this is where the 1 day response was. Of course, now we're 20 days later, 28 days later, so the response has kind of dampened significantly. And there's lots of carbon nanotubes in here. And then when we bring in the other materials, you see that many of these carbon nanotubes go nicely with Printex. And then also some other JRC nanomaterials go in there. The outliers or the high responders are basically nanosyl, carbon nanotubes, quartz, Mitsui, NM401, and asbestos should be, yeah, but we gave too little of a dose. So we would have had to shift over here to see asbestos come up. We couldn't give more because the animals did not tolerate higher doses. So ultimately, then you can define this hazard factor again relative to Printex as my reference material. You see 8-fold for quartz, you see like 100-fold for the carbon nanotubes NM401, which is a long and thick one, which are known to be highly toxic. Now let's move to inhalation, nose-only inhalation. Here we have 4 weeks of inhalation, subacute, 6 days per hour, 6 hours per day, 5 days per week, 4 weeks exposure, and then as a 3-day acclimatization period, and then you do the same thing, take the bar, neutrophil influx, and now you have the retained surface area, not the delivered, but what is retained in the lungs after that exposure. And here you see again, black is Printex 90 and titanium dioxide, P25. They are relatively close together, factor 4, as I said. I consider this still one tox class. And now here's my without specific toxicity tox class. And over here we have the high responders. And these are again NM401, Mitsui carbon nanotubes, and to some degree also NM403, which is really like a short and thin carbon nanotube. And if you look at the hazard factor, yeah, it's about 80. So overall, what we see is, and that was a big surprise actually, for the when you compare the hazard factors from inhalation after this 4-week exposure, 3D, 3 times weighting, and installation after 20 days, you find that for NM401, this hazard factor is really very close in both instances, about 180, while for quartz, inhalation shows a much stronger response, yeah, 80 versus just 8 for installation. But nevertheless, it's quite surprising how well installation can simulate inhalation. Of course, not perfectly. So now, this is the overall picture on the data, and I do this just for the day 1 installation data on the y-axis. Now you have this neutrophil part. I'm just plotting the slope now so that we get all the materials on one graph. So here is the slope, and this medium intrinsic toxicity class is this part here. You see, this is where most of the particles are. This is what I call the material without intrinsic toxicity. Then you have quite a few materials with lower toxicity, and you only have a very small number, like 6, which have a high or a very high toxicity. So what are these guys? Yeah, so over here we have carbonaceous materials, carbon nanotubes basically, and Printex, of course. And on the left side, ROS is on the x-axis, so with low ROS values, you find metal oxide materials, and the high responders are just zinc oxide and quartz, and asbestos, Mitsui, and NM401. Yeah, that is kind of relatively simple. Out of these 60+ materials, we have just 6 high responders and a few low responders, like graphene, for example, sometimes has a very low response. ROS is not very predictive for that. You see, it's a horizontal line basically, but what ROS does, it can tell you whether it's a metal oxide type induced inflammation or whether it's a carbonaceous type induced inflammation, because for higher ROS values, you're more in the carbonaceous regimes. For lower, you're in the metal oxide regime. So yeah, it's not a good predictor quantitatively, but you can at least discriminate between carbonaceous and metal oxide. So here's the effect, the issue of installation, very different in terms of distribution in the lung, inhalation uniform, installation not. Does that have an effect on the biological response? Here we have Printex 90 at day 1 again, neutrophil influx. Blue is the installation data, and brown is the inhalation data with the ventilator-assisted inhalation, yeah, where we have within a few minutes, we have the dose in. So very similar dose rate as for installation, and you see that they mingle very, very closely. Yeah. So that is, I think, the first proof that the difference between installation and inhalation does the dose, if you keep the dose rate right, you get about the same response, at least for Printex 90. So although the distribution is so vastly different, apparently the biological response is quite comparable. And then for nose-only inhalation, of course, you need to go with much higher doses because it's a much slower process. But if you then scale installation data to 28-day later, yeah, if you just let cool the animals down for 28 days, they get about the very same response, not for all materials, but for some you get the same response. So you see that installation is not affected by the distribution so much in the lung, as long as you keep the dose rate right. And installation can predict the subacute nose-only inhalation if you wait 28 days. And then if you do in vitro studies, you will find, and I'll show you that soon, that you need even higher doses if you do in vitro studies, about 10-fold higher than for the nose-only inhalation. And that is now my last slide here. So I'm trying to bring everything together. So I'm plotting now the IC50 value in surface area of material per surface area of tissue or lung. And we have in vitro and in vivo data. In vivo is here on the right-hand side, 3-day, and this is all the in vitro stuff. And I start on the right-hand side. Of course, the gold standard is rat in vivo inhalation. And you see, or maybe I should start here with the Printex 90 material. You see the doses for rat in vivo is 1 square centimeter per square centimeter, IC50. But then if you go to acute levels after installation, it's about a factor of what, 10, 15 lower. And if you go to the cell levels where you see the response from the cell side, you have to go about a factor of 10 higher. So if you can compare the dose from installation, 1 day acute response to the cell levels, you have a factor of 100 higher dose you have to apply to the cells in order to get a response. This is the IC50 level again. But what you see also here, green means this is the lowest hazard ratio, 1 to 4. And then the color coding, this kind of color is 4 to 16, then orange is 16, 24, and very high is above 64 hazard factor. And then, of course, you see here the gold standard. So Printex is, per definition, the low response. And then you have very high response from all the other materials we tested. And very similar, as I said, for the 28-day mouse installation data, you get a very similar pattern. And even for the acute response, you see that you get they're all in one group. They have less high factor of hazard, but they all group in the same group. So there's a lot of similarities for the installation and inhalation. Now let's look for the in vitro assays. So for in vitro assays, if we take as reference the rat inhalation data, the best performer here is the macrophages, the murine macrophages. They get 2 out of the 3 where we have data for, basically. And then if we take reference the acute inflammation from mouse, then the epithelial cells seem to do a little better. But overall, I mean, just note that they all go the right way. Printex is always the lowest, and all the other materials are high responders. All of these methods and models predict this in the same way. So in summary, surface area is a powerful dose metric, not just for spherical, but also for many fiber-like nanomaterials. So then if you do it based on this dose metric, many of the materials just look alike in terms of inflammagenicity. And the delivered surface area dose facilitates the definition of hazard factors. Yeah, we had these 4 different hazard classifications based on hazard factors. And then, of course, once you have the tissue delivered dose, you can also translate from in vitro to in vivo onset doses, which is what we need for regulatory purposes. Installation, as I said, is a surprisingly good predictor of inhalation, at least in terms of inflammagenicity. In vitro cell viability is a very crude assay, I grant you that, but it's a reasonably good predictor for acute and for subacute in vivo inflammation. And of course, epithelial cells, macrophages, yeah, they seem to perform somewhat similar. Maybe macrophages more sensitive and more relevant for the long-term response. Then in vitro cell viability, that is very important for us to realize, requires about 100-fold higher dose per surface area tissue. That's important, yeah, the dose per surface area tissue than the acute inflammation response requires. So there's no way we can get with realistic doses anywhere near to responses with in vitro assays, at least not of the ones we were using here. The most relevant dose metric for chemicals is molarity, and the equivalent most relevant dose metric for nanomaterials is surface area. So I would highly recommend we adopt this as the most relevant dose metric. It will facilitate many of our discussions. The data were, of course, from various groups. The in vitro data were from our group. Tobias Stöger mainly was doing the biological work, of course. Then macrophages, the rat macrophages from Olivier Jobert from University Laurent. And cell-free assay comes from Ulla Vogel from Copenhagen. And also her in vitro installation data, obviously. And we did the mouse ventilator-assisted inhalation in Munich, and then we had the rat nose only inhalation data from Laurent from INRS in Paris. And with that, I will take your questions.